Hi and welcome. This video is part of a series of videos on solving the wave, heat and Laplace equations. In this video, I'll be interpreting and solving the wave equation for a Dirichlet boundary condition, while following videos will concentrate on the Neumann boundary conditions as well as some harder examples, as well as maybe getting into some Fourier series. The prerequisite knowledge in this video is knowing how to solve ordinary differential equations. You should know also what a trivial solution is and be at least somewhat familiar with eigenvalues and eigenfunctions. So let's get into it. Really quickly, just before we get into it, I want to show you this summary sheet that I've made up for the wave, heat and Laplace equation. You'll see that the example we're doing today is the wave equation, so our PDE will have this form. We will get two homogeneous boundary conditions, and then we'll also have two initial conditions which may or may not be homogeneous here. Our separable ODEs are going to take this form. Our eigenvalues, if we're having x equals 0 and x equals L, our eigenvalue lambda will take the form of n pi over L, where n starts at 1 here. You'll see that if we have Neumann boundary conditions listed below, our eigenvalues, n, will start at 0 here. The Dirichlet boundary conditions, for our eigenfunction x of n, will take on a sine function, whereas if we have Neumann boundary conditions, we will have a cosine function. Our associated eigenvalues, t of n, will take this form here, and you'll notice that if one of our initial conditions is homogeneous, if it's a zero displacement, so we're not talking about derivatives here, it will have a sine value, whereas if we have zero velocity, so u of t for our initial condition, we'll end up with a cosine function. And then our eigensolution is just going to take this form, which it does for all of the wave, heat and Laplace equations. So just notice like the sine and cosine and the n equals 1 and n equals 0 across while we're solving the wave equation. So let's get back to it. The first thing you're going to want to do is step 1, interpret what is going on. So the wave equation u here is talking about the displacement, whereas c is talking, c is the speed. U of t will be the velocity, and here you can see we've got Dirichlet boundary conditions. All that means is that these here aren't derivatives, so this is our boundary conditions, and these are our initial conditions here. So the Dirichlet boundary conditions just means we don't have derivatives here. And all that means is if, say, we're modelling a rope, the wave equation can be used for a lot more things than a rope, but let's just assume that it's a rope. Say there's two people holding a rope. There's a momentum going through the rope, so it's going to make a wave. And both people are holding the ends really, really tightly. So the Dirichlet boundary conditions just means that both ends are fixed tightly. And if they're homogeneous, it means they're fixed at 0. So on a graph, it means the wave, we don't know what it's doing. We're not told that information, but we are told at x equals 0 and x equals L here, it's at 0. It's homogeneous, it equals 0. So that's what it's told. The two ends are fixed. Whereas if you're working with Neumann boundary conditions, the ends are allowed to freely vibrate. Or if you've got these people here, they're holding it really loosely. So the wave modelled is going to look a lot different to it modelled with the people holding really tightly. The two waves are going to look different. So we need to know these things. So here we have the ends are fixed, and they're fixed at 0. Right, so step 2. To assume the solution takes the form of u x of t equals x of little x big T of little t. So I'm using little x and little t here, and big X and big T. So you want to assume that the solution takes that form. Now, the solution might not take that form. There will be other solutions out there, very likely, that don't take this form. But what we're interested in is all the solutions that do take this form. And that's simply because we can use separation of variables if they take this form. So if the solution does take this form here, we can do step 3, which is where we plug solution into the PDE, the partial differential equation. And our PDE is, of course, the wave equation. So it is just the UTT equals c squared u of xx. So if we plug in this solution into the PDE, we're going to end up with something that looks like this, where the double prime is the second derivative. X double prime t. So step 4 use separation of variables. So the method of separation of variables, and I'm just going to write SOV for short. So all separation of variables is we want all the x variables on one side of the equation, all our t variables on the other side of the equation. Now, the way I'm used to doing it is to always put all the x's on one side and all the t's, as well as all the constants, on the other side. And that's just because then you're going to always end up with the same boundary equation. And so if you do something wrong, you will be able to spot it a lot more easily than if you're constantly changing the way you write it. So using methods of separation of variables, you're going to end up with something that looks like this. So my c squared, my constant here, is going to belong on the side with all the t's. And I always write it like this. And then we're going to end up with something, it's equal to something k. We don't know what k is. In this case, though, we do know that if you have Dirichlet boundary conditions or Neumann boundary conditions, k can't be greater than 0. So k can be greater than 0, but you're just going to end up with the trivial solutions. So k greater than 0 always gives trivial solutions. And we don't care about trivial solutions because they don't tell us anything of importance. They don't tell us what our rope is doing when it's doing anything interesting. It really only tells us what our rope is doing when it's not doing anything. And we already know what it's doing when it's not doing anything. It's not doing anything. So we're just going to not care about our trivial solutions. So in this case, we can write that, and therefore we can write k is equal to minus lambda squared. So it means we're always going to end up with either something negative or 0, or k equals to 0. You'll come to know when you do more of these that when you're working with Dirichlet boundary conditions, the k equals 0 case will give you the trivial solution as well, whereas a Neumann condition, it won't. So in this case, I'll show you what I mean a bit later on, and in the next video when I work on a Neumann boundary condition case, you will see more what I'm talking about there. So separation of variables. This equation here is going to give us 2 ODEs, ordinary differential equations. It's going to give us x double prime. Remember, this is equal to minus lambda squared, so I'm just going to talk about lambda from now on. I'm not going to talk about k. So plus lambda squared x equals 0. And it's also going to give us t double prime plus lambda squared c squared t equals 0. So these are our two very important ODEs that we'll be using. We're going to use this one for our boundary conditions, and we're going to use this one for our initial conditions, simply because our boundary conditions are concerned with x and our initial conditions are concerned with t. And they're two completely separate things. So you'll notice there are no t variables in our x equations and there are no x variables in our t equations. And we can say that this equals to something k here. And if it does, this just means that our t and x are completely independent of each other as well. As I just said, there are no t's in with our x's and no x in with our t's. And so if they always equal to each other, even if we let x's vary and the t's vary as they wish, it sort of means it's just equal to like some constant k. In this case, we're calling it lambda, negative lambda squared. So that's sort of just a bit more of an interpretation of that as well. So now we have these two ODEs. We're going to concentrate first on our homogeneous boundary conditions, and then we'll focus on the homogeneous initial condition that we've been given, and then we always save the non-homogeneous condition till very last. So firstly, what step are we up to? Step 5. Boundary conditions. So we know that from our prior training in ordinary differential equations, we know that this has the general solution in the form of x equals a cosine lambda x plus b sine lambda x. So that's sort of the prerequisite knowledge, that we should know this. So once we've got this, now we're going to actually use those boundary conditions. So in the boundary condition here, we've got our x equals 0 and our x equals L, and both of those are equal to 0. So we're going to put in x equals 0, and if our x's go to 0, we know that the sine term will vanish, so we're going to end up with a cosine lambda x is meant to be equal to 0, and this can just imply that a equals 0. And then the next one is L, so x of L, and just remember that a is still equal to 0. So using this general solution up here where a equals to 0, we're just left with a b sine lambda x, and that should also equal 0. Now, as I said earlier, we're really not interested in the trivial solution because it doesn't tell us anything interesting. So if we let b equal to 0 here, we're just going to get the trivial solution. So what we want to do is we want to let b be anything other than 0, but this here equation here should still equal to 0. So that just means that for here it implies that our sine lambda x should equal 0, which can further imply that, it's not x, it's L. We're doing L here. Our lambda L should equal to pi n, where n is an integer. So if we just solve for this, we have pi n over L. If we solve for lambda, for n equals 1, 2, and so on. This here, it starts at 1 simply because, as I said a little bit earlier, for the Dirichlet boundary condition, when k or lambda equals 0, we're going to get the trivial solution again as well. You can sort of prove that to yourself, but that's maybe like another separate video. So because that equals 0 is also the trivial solution and we don't care about the trivial solution, we're starting at n equals 1. But if we had Neumann boundary conditions, this eigenvalue here, so this is the eigenvalue, this eigenvalue here would start at n equals 0, 1, 2, and so on and so on. But for Dirichlet boundary conditions, it starts at 1. So, all right, now we can write, now we've put in our two boundary conditions, we can write our x of n, so this is sort of like our general solution now that fulfills both of those conditions. X of n equals b of n sine lambda, and lambda is pi n over L, and then x. Now b of n is just some constant, and this is a eigen function. So eigenfunctions often aren't written with a constant in there, but you can leave it in there. It's still correct either way. So I often leave it in there, and then I'll sort of show you why later, because we do need constants in our solutions. So I just leave it in, but it's up to you what you want to do. The next thing we want to do is work with our t variable, so for our initial conditions. So step 5, so this will be step 6. And these are our initial condition, the homogeneous one. You might not be given a homogeneous initial condition. You might have like 2 non-homogeneous ones. So that's a little bit harder, but still, in this case anyway, we have a homogeneous one. And probably most of you will have them as well. So our equation was t double prime plus lambda squared c squared t equals 0. And this has the general solution of t equals to a cosine lambda. Lambda, we know what lambda is now though, so it's pi n over L, and this will also have a c and a t because what's in here, plus, so again, this is a prerequisite knowledge. Should know sort of like where these are coming from. Pi n c t over L. Okay, so and then the homogeneous condition we were given up here is when t equals 0, it equals 0. So let's put in t of 0. So our whole sine term is once again going to vanish, so we're going to end up, the cosine is just going to also go to 1, so we're going to end up with a equals 0. So our solution here, our t of n, equals to b sine pi n c t over L. So if we remember at the very beginning, we assumed that our solution took the form, so that was step 6, so I'll do step 7. Our solution took the form of u x of t equals big X of little x, big T of little t. So now we know, and if it's, we'll do u of n because n can be the different integers, and we don't know what n is yet. So we know what x of n and t of n are now. So if we write our u of n equals our x of n is up here, and then we have, I'm just going to, so right here you're going to see that I've got a constant here and a constant here, which should have an n. They're just going to multiply together and create a new constant. So I'm just going to leave this being called little b of n, but that little b of n is not the same as this b of n here, so just take note of that. It's not the same. It's just another different constant. So we've got b of n sine pi n over L x, and then our t of n is this one here, sine pi n c t over L. And this is 4 n equals 1, 2, so on. Now, that is sort of like a general solution, but we have this other initial condition up here, and we need to work with that as well. So currently, the solution that we do have fulfills the other 3 conditions, but we also need it to fulfill this last condition here as well. So you'll notice that this one is a derivative here. So the first thing we're going to want to do is take the derivative with respect to t. So I'm going to write step 8, the non-homogeneous initial conditions, which is u of t, x of 0, I think, 3 sine 2 pi x over L. 2 pi x over L. Okay, so the first thing we want to take the derivative of u of n with respect to t, and that will equal b of n pi n c over L sine pi n x over L cosine, always get that mixed up, cosine pi n c t over L. So that's the derivative, and now we're going to plug in the initial condition, which is t equals 0 and x equals x. So at t equals 0, the cosine is just going to go to 1, so we're just going to end up with pi nc over L sine pi nx over L. Right, so what we need to do now is set this here equal to this, because of this and this, they're the same. So I'm just going to write them. And then what we'll be aiming to do is solve for the constant, the b of n, and we also want to solve for whatever n is. So we're interested in n and what the constant is, b of n. So we've got b of n pi n c over L sine pi n c over L. So we want to know n and we want to know b of n. You'll see that it's pretty easy to see what n is. N is always pretty easy to see. Well, the examples that I've ever been given, it's always easy. You just match it to the left-hand side. So you'll see that n is 2. So we just need n to be 2 here in order for them to match. So we can write 2. And then it's simply just solving for b of n. So if we have 3 sine 2 pi x over L equals b of n pi 2, remember n is 2 now, over L sine pi 2 c over L. If we divide by the signs, that's just going to go to 1. So we'll end up with 3L over 2 pi c equals b of n. And that's our b of n value. So now we can use this equation up here, this one, because that fulfills the initial condition here. So it's just going to, the final solution is this, and it's now u, it's not u of n because we know what n is now. N is 2, so we'll end up with u equals 3l 2 pi c sine 2 pi x over l sine of 2 pi c t over l. So you'll see that we've left the x's and the t's as they are, and we have filled in what the constant is and what the n is. So this is our specific solution. And this satisfies all the conditions listed at the top here. So I hope that sort of made some things clearer. So if you remember back to what u was the displacement and t was the time and the displacement going along the x-axis. So you'll now be able to see that this here, all of the work that we've done, now models our rope through time and space. So that's pretty cool. You can also model things like sound and vibrations and all sorts of things with the wave equation. So it's one of the very important tools in physics as well as maths. It also models things like how the traffic moves and a whole heap of other stuff. So if you liked this video, let me know. If you found it helpful, let me know. If you thought I wasn't very clear on something, also let me know and I'll try and clear it up and try and do better in the future. So thanks for watching.